started again. So, okay, that's fine. We already ran through this, so we'll just look it up again. We already introduced the BCD code, the weighted and non-weighted. And for the binary coded decimal, then here's the VHDL implementation of the BCD. Well, we'll try to run them. And this is the same, but at this here, in this implementation, we actually use combinational logic circuits. So you see that we do not have the clock signal like we have in the sequential logic implementation. So in this case, we have a clock and a reset because you could implement this using flip-flops, but using the combinational logic, so all we have is the input and the output, and we define our variables. Okay. So the same here for BCD to decimal implementation. And then we also have the binary or BCD to binary coded decimal to decimal. So we have that. Then we could also work our way through for the decimal using the same approach. We also convert our decimal to binary. So we have to divide and then we carry, right? So I'm just trying to run through what we already know. So this is the code, the VHDL implementation for the BCD to binary conversion. And here also, we have the weighted binary code for converting binary to BCD. Okay. So just like I mentioned, this is the 8-bit position. So we know each bit has a weight. So we know this has a weight of 128. This has a weight of 1. This has a weight of 2, 4. This has a weight of 8. This has a weight of 16. This has a weight of 32. This has a weight of 64. That is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. So that is 128 plus 8 plus 2. That's that. Then for this, that will be -1, -2, -3, right? So to the power, okay? That's to the power. So if this is 0, if this is 0, okay. Now, so once we say that's 2, so that will be 1 over 2, 1 over 2 to the power of 2, 1 over 2 to the power of 3, right? So this would be 1 over 2, which is 0.5, and this would be 1 over 8, right? Which is 0.125. So once we add that up, we're able to get, 138.625, okay? So that's converting to decimal. And then we could now each bit position, we now take 4 bit spaces for the BCD. So this will now be, so recall 8421, right? So where we have 3, so it means 2 and 1 are turned on. For this, just 1 is turned on. Then for 8, so it means just 8 is turned on. Then for this point 6, 4 and 2 are turned on. 4 plus 2 is 6. Then for this, which is 2, just the bit position 2 is turned on. And for 5, 4 and 1 are turned on. Yeah, so that's how we got this. Then we also have the VHDL implementation. That's from binary to BCD. So let's move this. So, okay. So this is all clear. Yeah. So we also have this as the implementation. Then we have other, weights. So this is 8421 BCD, 4221, then 5421. Okay. Then for the non-weighted binary codes, we have the SS3. So what this does is to add an additional 3 to what we have. So if we are in the decimal, so the SS3 code will be the actual decimal value plus 3, so that will give us 9. And once we convert 9 to binary, so we have the SS3. Plus recall your 8. Oh, sorry for that. So recall your 8421. So for your binary, regardless of, we're not talking BCD now. So we have 9. So 6 in decimal. So SS3. So this is SS. It's in SS of 3. So what it means is that we have to add 3 to it. So 6 plus 3 is going to give us 9. So 8 and 1 are turned on. So that's why we have this. Then 2, 3, 2, once we add 3, then that's 5. So it means 4 and 1 are turned on. So this becomes the SS3 code. Okay. Then we have the VHDL representation for the decimal to SS3 conversion. So we're able to define our input here is in decimal, then we have SS3 as our output, okay? So we also have BCD to SS3, but in this case, we have the BCD code. So what we now have to do is to add 3. So what is 3 in BCD? So we have 8421 BCD, for instance. Now 3 is 0011. Okay, so it means we are going to add 3 to whatsoever BCD code we have, and then we arrive at the SS3 code. Okay. So, and we also have SS3 to decimal. So for us to move from SS3, so SS3 is already in SS of 3. So for us to move to decimal, we have to subtract 3 from the SS3. So once we subtract 3, then we have the actual value. So that's what we just did here. So we subtract 3, then we have the actual value. So once we have this, then we cannot convert to decimal. So we also have the implementation. They're pretty straightforward. So BCD input, that's our aim. So we are using the vector space because we have to extend the number of bits. So we are using 4-bit position here, while they are 4 bits. So BCD is 4 bits. So the XS3 variant should be also 4 bit, should be 4 bit as well. Then we can perform our conversion. So this is SS3 to decimal. Okay, so our input is SS3, then our decimal value is the output, and then we have the gray codes. Now, one interesting thing about the gray code is that just like all that, it also runs on an algorithm. So the algorithm is pretty straightforward in the sense that the left bit of the same, or better, the left bit is the same for the gray code and the binary if we're converting from binary to gray. So if we're converting from binary to gray, so we want to retain the left bit, then we add the most significant bits to the bits on the immediate right, and then we neglect carry. So we'll continue this process until we get to the least significant bits. And the gray code number will always be the same number of bits as the binary number. So it will not be more than. So if we have 4 bits binary, we're going to have 4 bits gray. If we have 10 bits binary, we're going to have 10 bits gray. That's what we need. So let's look at how this works. So this is what we mean. So in this case, we have the binary 0010. So what I'm saying is that for the gray code, we are going to retain the same first bit is 0. And then we now move this to the next bit position and then add them together. 0 plus 0 is also 0. So, but should there be a carry, we'll neglect the carry, okay? So then we'll move this also. So 0 plus 1 is 1. Then we'll move this 1 plus 0. So there's no carry here. So everything seems to be pretty straightforward. Let us try the next example. So we retain the first bit. This is 1. Now we move this to the next. So 1 plus 0 is 1. Then we move this also, this next bit. 0 plus 1 is 1. Then we move this next bit. Then 1 plus 1 is 2. But we are actually working in binary. So it's 2. So 2 divided by 2 is going to give us 1 remainder, 0. Right? So we are going to neglect every carry. Then our answer here is 0. Okay? So 1 moves up this way, and that's 1. So let's try the next example. So things get, so as to clear things up. Well, this is the code implementation. So we have the for binary to gray. So we have the binary input. Then we have our gray output. And that runs is pretty straightforward. Now, the same applies when we have to convert from binary to gray. But the algorithm, there's a little tweak. So let us look at this. So for converting from gray to binary, now the first bit is usually the same, so we retain it. Then we now have to move that bit upward such that we now add. So 1 plus 0 is 1. So what we have here, we'll move it up this way. 1 plus 0 is also 1. What we have here, we move it upward. 1 plus 1 is 2. That 2 divided by 2 is 1 remainder 0. So we have our remainder as our answer. Now, in this case, we do the same thing. So we are retaining the same bit for the first bit position. Then we move the first bit position upward to the next row, or the next column rather. 0 plus 1 is 1. Then we move this one up this way. 1 plus 1 is 2. So we have 0. That's 2 divided by 2. That's 1 remainder 0. Then 0, 0 plus 0, 0, 0 plus 1, 1. 1 plus 1 then is 0. Okay. And the same way, we have the gray to binary implementation. And I think that's that. So I just had to run through this so we could begin our class interaction, because quite a number of groups will be making their presentations today. Okay. Now, before I shut this down, I think I want to share, where's the model scene? Okay, I think I want to share the models. So let's see, what do we have here? Okay, okay, gray to binary. Let's let's open gray to binary. Okay, that's a project. I don't want this, I don't want this. This and simulation. I think I want to close all of these projects. Let's close all those projects. Then let's see if we can open gray. Where's this now? This is SS3. So what I need for my project is the SS3. Mhm. Okay. Okay. So that's what we have here. So we're going to take a gray code and then we land. So let us add this to the wave, for instance. So everything is in hexadecimal. Okay, well, so let's assume I'm moving from gray to binary. So let's force this. Let's say 8. So let us simulate. So that's that. So what if I change this to binary? Perfect. So yeah. So if I should also change this to binary, what's this? No, let's change the radius to binary. So perfect. So we're in good shape. So if you change the first bit and that moves up 1 plus 1, then that moves up 1 plus 1, that moves up 1 plus 0, 1. Yeah, perfect. So it means this is running. So let us see if we can play with. Hope you got that straight, because we're just trying to see if all of these. So let us end this simulation, and then.
No, sir.
Okay, well, I'm just trying to, we just display the codes and the slides. I'm trying to run through because you guys have to make your presentations. Now, I just played with the simple gray code, right? This is just, okay, I already cleared it. The simple gray code, which is this, okay? And, okay, let's try another one. Let's try another one. Let's try SS3. I think I have some SS3. Is this now? Okay, decimal to SS3. Okay, let's try this. So we're going to add this to wave. Add to wave. So here we are taking the input decimal and we want to get SS3 output. So let's see if that works. So now the radius here means is more like how we want our code to be represented. So by default, right now, my system is on hexadecimal. Okay, so we see HX. So we could always change that, but let us input. Let us force input here. Let's say I have 8. So what am I going to get for my? Yes, okay. So I got B. So let's change this to binary. That. Good. So now it's SS3, right? Now, if you recall, from what we already mentioned, for SS3, we are actually adding 3 bits to it. So I gave an input of 8, and looking at our 8421 code, so an input of 8 is 1000, right? Because this bit position is turned on, so that is 8. That's our decimal. Now the SS3 is going to add 3 to it, so that is going to be 1011, right? And that's what we got here, 1011 as our output. I don't know if did you get this now? Is this clear?
Not really, sir. You said we converted from what first to decimal?
We are converting from decimal to SS3 code.
Okay.
So we are now to convert to SS3, so it means we are adding 3 to it, right? It's in
Yes, sir.
SS3. So now 8 in decimal is 1000 in binary, right?
Yes, sir. Yes, sir.
So now 3 in binary is what? So that's 8 is 1000 in binary. Now 3 is what? 0011, right?
Yes, sir.
So if we add this up, that will give us our SS3 code, right?
Yes, sir.
Yeah, our SS3 code. So that will be 1011, and that's what we got here. That's our output.
Okay, sir. Okay, sir. Understood.
Yeah, exactly. So that's what I mean. And this is the code, we compile to do that. So we have our decimal input, the standard logic, then the SS3 code as the output. So the architecture is to process, decimal input. So here, these are just comments. We want to convert the decimal input to integer and add 3 to it, right? So SS3 output will be this to unsigned, so to integer this, and then we have +3, okay? So then we end process. So we are just trying to play with whatsoever we have. Well, that's fine. I think someone already mentioned that we should try to, come up with a tutorial set on VHDL. Okay, well, we'll do that. So we're just trying to play with the essence is you should be doing hardware programming. Okay, and the hardware programming we want to play with is either to play with sequential logic or combinational logic. And most of the activities we run will be sequential. So we have to assign a clock. We'll be playing with flip-flops. Okay, let's just put it that way. Playing with flip-flops. And for us to be able to achieve whatsoever we want to achieve, then we just need to figure out a way to bring it on board. And we already know what to do when it comes to translating our design to using the VHDL tool. I think that's just it. So I think we can now go straight into our presentation, right? But is this clear? Is this clear enough for now? Hello?
Hi.
Yeah, so is it clear for now? I think it's in good shape for now.
Not sure, sir. Not sure. But then
just please express your doubts. No, express your doubts. Let's take them so we know what to do. Because your feedback at this point is going to be very valuable to us. So we know what to do to make things better for you. So what are your doubts? Please share. So let's take another 5 minutes to just express our views, okay? Go ahead, please, Oladayo.
Yes, sir. Sir, can you please explain gray code to binary code again? I think I did not grasp that.
Okay. Okay, gray code to binary. Okay, let's go back to the notes.
From binary code to gray code and the gray code to binary. So
okay. So this is gray to binary, right? This is binary to gray. All right. Okay. So this is the idea. So we have the binary 0010. But mind you, this is running on an algorithm. That's this, okay? Now, the algorithm for converting gray code to binary, that's what we have here. So let us look up for, let's start with this. The algorithm for converting binary code to gray code. So it says the left bit. So we have, let's assume we have 100101. So now looking at this is my left bit. This is my rightmost bit, right? So it's saying that the left bit is the same as the gray code, or better still, is the same in the gray code as the binary. So it means that if this is my binary, and I have to convert to gray code, so my gray code, for my gray code, this leftmost bit is still going to be the same. So all I need to do is to drop it down. Okay, it's the same. So we are not changing that. So then the next point is that you want to add the most significant bit to the bit on its immediate right and record the sum. Neglect any carry below in the gray code. So it means that I want to move this to this point. So that's what happened here. Okay, so move this to that point. So I want to move that to this point. So if I move this to this point, so that's 1 coming here. So 1 plus 0 is also 1. So I want to move, then I now have to move this again to this. Take note, it's not what we got as the gray code equivalent we are moving. That is what we do when we are converting from gray to binary. But now we're converting from binary to gray, so we're only moving this to this. We add whatsoever is in excess, we don't move to the next like we do in regular addition, we neglect it, right? And then 1 plus 0 will now be this. So this is 0, we move it to this 0. 0 plus 0 is also 0. Then we move this now to this, so that will be 0. 0 plus 1 is 1. Then we move this 1 to 0, so that will be 1 plus 0 is 1. Then we move this 0 this way above 1, so 0 plus 1 is now 1. So the gray code here will now be 1 1 0 1 1 1. So that the gray code in this case, I think let us correct this. So the gray code number will always have the same number of bits as the binary. So let's assume we added, and then we now had one remainder, 1 or whatsoever. So whatsoever it is, we are not interested. So we have how many bits here? 1 2 3 4 5 6. 1 2 3 4 5 6. So that's the equivalent. So that's what we did here. Okay, that's what we did here. So the same applies here. Okay. Now for the, is that clear? Is this clear for binary code to gray code?
Yes, sir.
Yes, sir.
So now let us move to where this is, we just played with this now, we ran that. Now let us move to binary to gray. So where this is the algorithm running, saying that the left bit is the same as the binary, okay? The left bit for the binary is the same as the gray code, I mean. Now the most significant bit is transferred to the top of the most significant bit of the gray code, okay? Because now we are moving from gray to binary. So that's the only tweak here. So that's the only difference here. So let's move this. So what we are saying here now is we have this as the first bit, we are retaining that. So the binary bit, we now move it upward You know, when we're converting from binary to gray, we moved this bit this way, right? But that's not what we are doing this time. We are moving the binary upward, not this. Does that make sense?
Yes,
Yes,
sir.
sir.
So then we add this. So 1 plus 0 is 1. Now, if it were to be from binary to gray, we would have moved 0 this way because this is 0. But instead, we are moving 1. So if you apply the algorithm for binary to gray, for gray to binary, you're going to get the wrong thing. So we're moving 1 above this time. 1 plus 0 is 1. Then we're moving now. If we're on binary, we would have moved this, right? Which is not, because for gray to binary, we are moving this time to this. You get the point? Is that clear?
Yes, sir.
Yes, sir.
Okay. So any other thing you want us to talk about? Okay, so I'll stop sharing. So I think now we'll call on group 7 to make their presentation. Group 7, please. Can you please share your slide? Is group 7 absent?
So we're here, sir.
Okay, please,
So
please share your slide, okay? Okay, it's like they are not ready. So let us move to group 5. Do we have anybody in group 5?
yes, sir.
Please share your slide. Okay, this is group 7. Okay. So
Yes, sir, group 7.
yeah, so what's the presentation title? Okay, go ahead. Go ahead, please.
All right, sir. Next slide. So, good morning, sir. Good morning, class. Can you hear me?
Yeah, sure, we can hear you.
Yes, we can hear you. Good morning.
All right. So, we're talking about advanced code conversion and encoding techniques. So, code conversion. What is code conversion? So, code conversion is the process of converting or transforming data from one code form to another for compatibility and efficiency. So, and then what is encoding? Encoding is just a way of representing data in a specific format for transmission, storage, and processing. So, next slide. So we come to the introduction to error correction coding. So what is error correction coding? It's a method to detect and correct errors in transmitted or stored data. So as there can be error, yes, there might be errors when transmitting data. So the error correction coding is used to detect and correct errors in transmitted data. So it is important because it ensure reliable communication and storage in the presence of noise or faults. And it is widely used in digital communication storage devices and fault tolerance systems. Next slide. So one of the error correction coding is the Hamming code. So the Hamming code was introduced by Richard Hamming in the year 1950, and it's the simplest form of error correction code. So, and it detects and corrects single bit errors in transmitted data. So it works like, okay, how it works? It uses parity bits placed at specific positions, and the Hamming code, the Hamming distance defines error detecting and correcting ability. So we have numerous areas where we use Hamming codes. So we use it in early computers for error correction in RAM and communication protocols. Next slide. We also have the Reed-Solomon codes. So it's a non-binary cyclic error correcting code, and it corrects burst errors across multiple bits. So it finds its application in CDs, DVDs, QR code, and deep space communication. So its advantages: it is effective in correcting large error patterns in data blocks. Next slide. We also have the low density parity check. The low density parity check codes was developed by Robert Gallagher in 1960. So in the 1960s, but it was later refined. Yeah. So the key features are sparse parity check matrix for efficient computation, superior performance close to Shannon limits, and it finds its application in Wi-Fi standards too, and satellite communication system. So I'll pass it to the next person, sir.
Yeah, so the Huffman coding is next slide. Huffman coding is a compression algorithm that uses various lengths of code. It uses Huffman coding it uses various lengths of code. So there are various steps. It first counts the frequencies of the characters, then it builds a binary tree, and then assigns shorter codes to more frequent characters. You can use it for image compression and zip file and for text data. Next slide, please. Then there are various compression techniques. We have the lossless compression that retains the original data perfectly, and the lossy compression that reduces data while also affecting the quality of the data. Then we already mentioned the techniques that were used before, like Huffman, arithmetic coding, and dictionary-based methods. So now, next slide. So now, gray code. Gray code is a binary numerical system where two successive values differ by only 1 bit. We use gray code to reduce errors in the digital systems during transition. And with their various applications like rotary encoders and analog to digital converters. Then there are also applications like signal processing and image encoding, which reduces pixel presentation during compression. It is also used in hardware systems to optimize circuits with high speed switching. So I'll be passing it on to the next person, Paula D. Complete the presentation.
All right. Good morning, everybody. So I'll be taking binary decision diagrams, short for BDDs. So what are BDDs? They are graph-based representations of Boolean functions, and we have nodes which represent the variables under consideration. And the pathing between those nodes are also represent logic. So what are some benefits of BDDs? They are used for compactorization of logical synthesis, which is the journey of logic gate, and they also facilitate efficient algorithm operations. So now I'm looking at some of the applications or where they're used. As I said earlier, they're used for logic synthesis, which optimizes digital circuit designs. They're also used to optimize code. All right. So by optimizing code, they improve execution efficiency in compilers. And they're also used for hardware verification, which ensures the correctness in hardware design. Now, integrating encoding techniques. Why do we integrate in the first place? The reason why we integrate, because we want resilience and also data efficiency. And some examples of integrated encodings are we have JPEGs or JPEGs for short, which combines what compression and what error control. And we also have MP3 format, which balances what storage reduction and audio quality. Now, what are the challenges in code conversion that we face? Some challenges we face in doing code conversion can be one computational complexity, which are the encoding and decoding, which obviously can be resource intensive. That means we might need a computer with lower computer and computer with lower specs. And some of the trade-offs are we have balancing efficiency, we have accuracy and speed. So now some real world constraints. We have the implementations in low power limited memory systems. Now we look at some of the future trends we have here are emerging technologies. One, we have the quantum error correction technique. We also have the artificial intelligence-driven data compression and coding systems. We also have the what enhanced performance, which are faster algorithms for LDPC and what Reed-Solomon codes, which are just techniques that we discussed earlier. And we can also look at the broader applications. Some broader applications here that we highlighted were the increased usage in what IoT, which is Internet of Things, and what edge devices. And this is some of our references that we use. Thank you. So that's the end of our presentation for Group 7.
Okay, that's fine. That's fine. Now, you made mention of Hamming codes, right? So can you explain to us the error correction capability of Hamming codes? Okay, I think they didn't get that. Okay.
Sorry, sir, can you come again, please?
I want you to explain to us the error correction capability of Hamming codes.
Oh, okay. So we have different types of the corrections. We have I think the single beat, which is where it's designed to correct just one beat errors. That is like if a single beat is flipped due to like let's say noise during processing, the code can what it can identify the location of the error. And we also have the 2-bit error detection of the Hamming code, which it detects what is not correct before 2 bits. That is, if 2 bits are flipped simultaneously, the parity checks would indicate an inconsistency. But in that sense, the code can't really print.
Okay, so summarily, what I would love you to pick from there is that the Hamming codes can detect up to 2 errors, but it is designed to correct single bit error. Do you get that? Do you catch that?
Sorry, sir, my network disconnected. I don't know where you guys lost me at.
Okay, now what I just said is that the Hamming codes are
Yes, sir.
designed to detect at least or at most up to 2 bits in error
Yes, sir.
simultaneously. Why they are designed
Yes,
to
sir.
correct single bit error.
Yes.
Yes, sir.
Okay. Now, which of the codes can be used to correct for multiple bits in error simultaneously? Like you mentioned it, among the codes you mentioned. Which of them? Okay, you are still thinking. Okay. Now, while they are still thinking, I want group 3 to put up their slides. Let us see. Group 3. So when we
So
have
do you say for
multiple,
multiple bits?
yeah, when multiple bits are in error,
So does read Solomon's
yeah,
code
well,
does use?
Solomon is used for burst errors, right? So let's assume we have 110000 and then 1100 are in error. So that's burst error, right? Then
Yes, sir.
yeah, Solomon will do that. Okay.
Thank
Now,
you, sir.
were you able to look up the lecture notes on information theory and coding?
Sir, I was I started the first one on finite fields, but I couldn't get to the error correction codes.
Okay. Please, you guys still have to do that, okay? Just try as much as you can to look
Yes,
up
sir.
notes, because
Sir.
yeah, because one, we've been able to cover the code conversion, then we're talking about encoding. And for us to be able to encode, we have to look at things from the communication perspective. So that will bring us back to Shannon, okay? And what he said about, yeah, good morning, we'll come to you shortly. And what he talked about in mentioning the source transmission and the reception. So we have two extremes. And for us to be able to transmit, then we have to figure out the ultimate data compression limit. That's why we'll begin to talk about the entropy. Okay. And
Yes, sir.
then,
Thank you, sir.
and then at some point we want to do encoding. Then for us to not transmit, then we have to begin to talk about the capacity. Okay. So what we want to push into the channel, does it have the capacity to take that? So we begin to talk about the channel capacity for the ultimate data transmission limit. Well, you get all of those in the information theory and coding test, because all we are all about in this course is playing with bits, right? Zeros and ones, how machines do all of that. So these two resources, the resources from both ends should be able to, assist. Okay, go ahead, group 3. Let us hear you out. So I would love you to present something new, okay? Not necessarily repeating what the previous group presented. Go ahead, please. You have the floor.
Morning, sir. Morning, sir.
Good morning.
Yes.
You're with the class, not with me right now.
Okay. So me and my group were able to work on this week's presentation, which is advanced techniques, coding techniques, and error correction. So next slide, please. So the introduction. So advanced code conversion and encoding techniques are like methods used to change data from one form to another. So these techniques are very important in areas like data storage, security, and communication. So they help to store data easier, faster to send, and they're compatible with different systems. So in this topic, we'll look at different encoding methods like Huffman coding, Reed-Solomon codes, and encryption, as well as how to convert data between different formats. So it's very important to understand these techniques as they help to improve performance, security, and ensure different systems can work together smoothly. Next slide, please. I'll pass it over to Jeremiah to explain Huffman Hamming techniques.
Okay. Hello, everybody. So we'll be talking about Hamming codes. So the purpose of Hamming codes was actually for the purpose of reducing errors during communication, during computing, and telecommunication. So it was invented by R.W. Hamming, who designed the Hamming codes for more efficient transmission of data during computing and telecommunications. So the Hamming code was actually designed to detect 2-bit errors and also correct single-bit errors. All right. So the concept actually, it employs the use of special coding techniques designed by RW Hamming, and where parity bits will be combined with the actual data that is in binary form. So the combination of the parity bits and the actual data is actually known as code word. Can we go to the next slide, please? All right. So the idea is that from the sender's end, the parity bits will be combined with the data bits. So let's say, for example, we have 4 bits of information that the sender is trying to pass to a receiver. What will happen is that before transmission, the data is combined with 3 parity bits. So when we have 4 data bits that we're trying to transmit, the combination of the parity bits and the data bits will form 7 total bits, and that is referred to as the code word. So a special coding technique was that RW Hamming developed a very efficient way of detecting bits, detecting the errors that may occur in transmission. So in a sense that the parity bits were grouped, and then those parity bits were actually used to check individual errors. So looking at that table that we have right there, we have for the first row, we see it is 1, and then the sequence to check was actually you check the first bit and then you skip 1 bit. So what will happen is that first bit is actually the first parity bit, and then the positions that are to be checked will now determine if there is an error or not. So based on the sender's choice, if it is going to be even parity or odd parity, that is what is going to make it possible for the receiver to detect an error. Ideally, it's usually even parity that is used. So the even parity is actually to add ones or zeros to ensure that the set of bits in a given sequence add up to a I'm so sorry. The even parity is used to show that the number of bits, the number of one in a set of data is even. All right. So the parity bits 1, 2, and 4 each have their own methods of checking with those sets. So the parity bit of 2 we check the set of 2, 3, 6, and 7. The parity bit of 4, we check the set of 4, 5, 6, and 7. Afterwards, if the parity bits don't correlate with the number of if the parity bits don't actually give even bits, if the parity bits don't sum up to an even parity, then that's the method the user is going to use to detect the error and make error correction. So after the error has been detected, correction will be made. I'll be passing on to the next person.
Good morning, everyone. And I'm Toby, and I want to just talk about your Reed-Solomon code. So your Reed-Solomon code, invented in 1960. Okay. The Reed-Solomon code was invented in 1960 by Sir Ivan Solomon Reed and Gustav Solomon in Massachusetts Institute of Technology, and it's a type of error correcting code that can detect and correct to an extent multiple errors within a block data. And it's most often used in your communication system and software, and storage system, whereby it takes in robust data and helps change from one form to another. So more about this is that your Reed-Solomon code is like a method of error correction based on polynomial algebra, which is built upon your Galois field. And what this means that it works on the operation of math. It works with math operation to perform error correction calculations, and it transforms your block data into polynomial, then carries out the addition or carries out your math operation, then changes it into, or rather it transmits it, then at your transmitted end, it takes in that data and just gets to remove the errors over time. So your RS code, like I said, it works over finite fields, which is your Galois field. Next slide, please. Sorry, can you hear me? Next slide. All right. So it works on a block length of n, which is your 2 raised by n minus 1 with a message size of k, and your parity check of n minus k, which is represented by 2t. And like I've said, the encoding process works on your polynomial algebra, and your parity check is generated by your parity check is done by evaluating that polynomial in your finite field. Then it goes down to your receiving end where the error detection begins with your syndrome calculation. So if errors are present, the syndrome just helps to construct a error locator polynomial using algorithms, and it then finds those error locations and removes them, recovering your original data. So like I said, your Reed-Solomon code is often used in the communication system or storage systems. For example, are your CDs, where some parts may have scratched, and you would want to recover some data on that CD. So your Reed-Solomon code is an example of a kind of removal of those error patches to recover the main data. So I'll be passing on to Tunji, who would explain more on the slide.
Next slide, Abeg. Yes, I'll be talking on LDPC codes, which are low density parity check codes. Yeah, so LDPC codes are error correcting codes used to improve reliability of data transmission and storage. So they rely on a mathematical structure called a sparse matrix. So the low density refers to the matrix sparsity, meaning most entries are 0, which makes the computation more efficient. Yeah, so the way it works is it encodes data into longer bit sequence with redundant bits. This redundancy allows error caused by noise to be detected and corrected. The whole process uses a parity matrix to define how bits relate to one another. So LDPC codes are important. They approach Shannon's limits, which is the theoretical maximum efficiency for error correction. They are fast and scalable, which make them crucial for systems like 5G network, where high-speed, reliable data transmission is critical. So the key idea is by using Tanner graphs, which use variable nodes, and the variable nodes represent data bits, and the check nodes represent parity checks that enforce error correcting rules. As you can see from the image there, that's a Tanner graph of parity matrix. Yeah. So Abekunle, next slide. Next slide. Yeah, so the decoding mechanism employs an iterative message passage algorithm on a Tanner graphs. Yeah. As I said, the variable nodes represent the data bits, and the check nodes represent parity check that enforce error correcting rules. Now, LDPC codes are used essentially in wire communication, which are 5G and Wi-Fi, data storage systems, which are the hard drives, and space exploration communication, which are the signals from spacecraft to Earth and etc. So, LDPC codes revolutionize modern communication by balancing efficiency and accuracy in error correction. Yeah, thank you. So I'll be passing on to the next person.
All right. Good morning, class. I hope you can hear me. So I'll be presenting on the Huffman coding. So basically, the Huffman coding is a run length limited code, which is prefix free also, that allows for lossless data compression. Now, what this means is that in certain word bits that have word or letters or bits rather with more frequencies, those frequencies are assigned shorter code values in order to allow for compression and lower memory use. So the working principle is, first, we determine the frequency of each symbol. I would love to give a physical presentation or a whiteboard presentation, but I don't think I can do that from my end. So I'll try to explain to the best of my abilities. So firstly, we determine the frequency of each symbol. Then we create a priority queue, or in other words, we assemble a forest. Now the forest is made up of
Just a minute, please. You want to use the whiteboard? Why not go ahead and write?
the option is not available from my end.
Okay.
I don't know if I can.
Okay. Alternatively, you could create a blank page on your PowerPoint and then use that as a whiteboard.
Okay, create a blank page on my. 1 second, please. Trying to do that. I think I should try sharing my screen to.
Yeah, so you could do that.
All right. 1 second, please.
Perfect. I think
Can you
we're
join
good
this?
now. I'm sure that's not the problem, right?
Now.
Okay. Can everyone see my screen?
Yes, you can.
I sadly still don't see an option to annotate or write on here. 1 sec, please. To be very honest, I still don't see an option to share, so I think I will just quit sharing and explain as I can.
Okay, I think someone just created a blank page for you where you could write and do whatever you want to do.
Check. Well, I'm using the
ahead.
web version, so I don't think that works here.
Okay. Okay, go ahead.
All right. So as I was saying, it's a run length limited code, and how it works is, first of all, we assemble each bit or each letter that is to be represented, and assemble a frequency table, sort of. Then we create what's often called a forest or a priority queue, which means we assemble the bits in order of frequency from lowest to highest. Then we begin combination. Now we combine by pairing any two bits of the smallest frequencies, right? So when we combine that, it comes a parent node is formed from the combination of those two, which is equivalent to the sum of the two bits. Now, if that two bit is no longer the smallest bit in the sequence or the hierarchy, we move it accordingly to its new position in the forest. So we continue pairing and moving each node until we have one single binary tree, parent node at the top. And the sum of the parent node is, or rather, the value of the parent node is the sum of all frequencies of all present bits. Now, to decode the message, we traverse the tree from top to bottom, from root to leaf for every single branch, and then take the code that comes from it. So branches to the left are denoted 0, branches to the right are denoted 1. So as we traverse, we take our respective values, either 0 or 1s, and then use those to represent the code. So how this is great for compression is that it saves the amount of space required, or rather saves the amount of memory required for each bit for each symbol that is represented. Ideally, or basically, the ARC system, which is most common, uses 8 bits per symbol. But using the Huffman coding, we can reduce the size of a every symbol or the most frequent symbols to so much as even 1 bit, therefore minimizing the minimizing the memory that is used to so much as about 20% of the original ACKI code. So next slide, please. So the applications of ACKI code, inherently, it makes sense that the Huffman encoding, it makes sense that the Huffman encoding is used for multimedia encoding, JPEG, PNG, MP3, video compressions. They all apply Huffman encoding. Many use them in 2 stages. The Huffman encoding is applied second after the LZ77 compression, which uses a 32 KB text window. Also, in file compression, the same format is basically employed. And also in data transmission, Huffman encoding is very useful because it can reduce or minimize the amount of data carried across a network, which conserves bandwidth, and also which I believe aids for more secure transmission, because the shorter a code is, the easier or the less likely it is to become corrupted during transmission. So next slide. Yeah, that's my bit. So I'll move on to the next person to present.
Okay, good morning, everyone. So I'm going to be talking on data compression technique. Now, the first one is lossless method. Now, this is reducing data size without losing any information. And basically, it's essential for text, code, and critical data. So now, there are several techniques that actually entails in this lossless method. And the first one is the Huffman coding. Now, this one is for short codes for frequent data, like for a code that is actually very short. Now, we have the zip, we have the JPEG, and metadata. Now, on to the next, we have the run length encoding. And this compresses repeated sequence. That's the BMP and the TIFF. Now, on to the next, we have lempel zip. Now, this replaces repeated strings with references. So a string that is actually repeated is actually replaced. Now, we have the PNG, we have the GIF, and the zip, and so on. Now, we have arithmetic coding. This actually represents data as a single fraction. So a data, it's just represent it as a single fraction to be able to be identified. Now, on the next one is Burroughs Wheeler's transform. This reorders data for better compression. So for you to be able to identify particular data, for you to be able to be in the right order, we actually use the Burroughs Wheeler's transform. Please, the next slide, please. Now we have the lossy and the hybrid method. Now the lossy compression achieves higher compression by discarding some data that is used in multimedia. So this context actually means data that are actually not needed in this, data that are irrelevant are actually being discarded, and the ones that are relevant are actually left. Now we have discrete constant transform. This removes less noticeable frequency component that is in the JPEG and MP3. Now we have discrete wavelength transform. This compresses using wavelets. As our example is our JPEG 2000. We also have perceptual coding. This actually means exploit limitation of human perception. That is our MP3. We also have factual compression. We uses factual for image coding. Now the last one is the hybrid compression, which combines the lossless and the lossy methods together. So for actually better understanding, for us to actually understand these three concepts, I think I will actually, for understand now, we simplify it. Just like for the lossless method, I'll use a suitcase, for instance. So it's like putting all your clothes, irrespective of the kind of clothes, into a suitcase. Then the lossy method means removing the ones that are actually irrelevant, the ones that are not useful, the clothes that are actually they are not needed from the suitcase, so that it will actually fit into that suitcase. And the hybrid compression actually means putting in sorting out the relevant one and the irrelevant ones from that your suitcase. That's just basically what these data compression techniques mean. I'm giving it to the next person to actually take over.
Good morning, everyone. Okay, so can you hear me?
Kunle,
Yeah?
Kunle.
Okay, I hear.
Yes, this.
Go on.
Yeah. Good morning, everyone. I'm Daniel Olawale. I'm talking about application of gray code in signal processing. As Dr. Ibasi explained, gray code is also known as reflected binary code, in short, RBC. It's a representation where successive numbers, like it's a type of binary number where successive numbers just change in one bit compared to the binary that changes in three, like 1, 2, 3, or even more. Characteristic of gray code is that, as I mentioned, single bit difference. Only one bit changes consecutive, like in a sequence. Only one bit changes as it moves on to the next one. Cyclic nature means that at the end of a gray code, for example, from from 1 to 8, which is 0 to 7. Once that the gray code ends there, you can go back to the beginning, and then it totally changes in one bit, which means it can continue from where it stops to the beginning without using more than one bit, without changing more than one bit. For gray code conversion, Dr. Abase explained that we'll add the a bit to the next bit. We won't consider the carryover. In my example that I added there, I used an XOR gate, which compares the two bits that's comparing. So if it's the same, it puts in a 0, and if it's different, it puts in a 1. So that's how it's also the same way as Dr. Bose explained, that adds the bits and then doesn't include the carryover. Next slide. All right. Applications of gray code in signal processing. A very common example is in rotary encoders. They are crucial in electromechanical systems for tracking rotational positions with precision. So we could use binary coding type for rotational encoders, but it is better to use gray code, because for binary coding, since it changes in different, you could change different bits at a time, which means when the encoder is reading the values, sometimes a mistake will occur where it could read two different values wrongly, and that is going to be something that's going to be a very bad error. So with gray code, it only changes one bit at a time, so it's easier to track errors, and even when there's an error, the error won't lead in a very big difference compared to binary encoding. It is useful even in noisy environments and high speed rotations. Applications of gray code encoders include robotics for joint movements and CNC machines where you need accurate tool positioning. My second example I also added was ADCs, analog to digital converters. When different bits are changing at a time, glitches will occur in the system that is monitoring the changes. So to avoid those errors, it is better to use gray code where only one bit changes. And another example is also the error detection in transmission. All in all, it prevents synchronization error over noisy communication channel. But all in all, gray code is useful in signal processing, whether it helps prevent errors from regular binary that changes in different bits at some point. So yeah, that's the application of gray code in signal processing. It helps to reduce errors. Quickly, can move on to your part.
All right, good morning, everyone. So
We can't hear you. Please, you want to speak up?
all right.
Yeah, we can hear you.
Okay.
Yeah.
Okay, let me connect to my phone. Maybe the laptop is not loud.
We can hear you clearly, actually.
We can hear you. We can hear you.
Okay, am I clearer now?
Yes.
Yes,
Yes.
yes.
Okay. So yeah, gray code in image encoding. So basically, we're going to be talking about how you can apply gray code in image encoding. So Daniel has already told us about like what gray code is. Basically, it's just a type of representation system where each bit differs by one. So that's like one of the very major things about gray code, and that's one of the things that makes it very good in detecting errors and just being used for processing generally. So image encoding is the process of converting visual information like our pictures and videos into digital data. We have common formats like JPEG and PNG. These are the ones that we see very regularly. There are some other formats of pictures, but maybe some of them are like the ones you have with maybe like raw photos you have on a professional camera, for instance. So you also have GIF, which is the one that allows some form of animation when you have like pictures that are moving and everything. So gray code is a special binary system where consecutive values differ by only one bit, reducing errors in transition. This property is valuable in various applications, including some related to image systems. So gray code is not directly used in standard image file formats like I mentioned JPEG and PNG. We don't have something like dot gray code or dot GC or something. But the gray code comes in the hardware part, and it comes in processes where you're trying to minimize the transition errors in like the whole image processing like process and everything. So let's now look at how gray code is actually used in image encoding. So number one, we have flash ADCs. Basically, this is image acquisition, flash audio to flash analog to digital converters. So this is when sensors capture image data and analog signals need to be converted into digital. So flash ADCs use gray code to reduce errors by multiple bit changes happen simultaneously. This ensures the image data we get is as accurate as possible. Again, it is the fact that when you're moving from one number to the next, only one bit is changing. That makes it very good to use gray code in handling errors. For instance, if you are going from if you're looking at normal binary, two can change, or maybe at some point if you have something like 0111 and then the next is 10000. Basically everything has changed, but with gray code only one is changing every time you move from one number to the next. So it's also used in image processing. So gray code enhances image analysis techniques like dithering and hashing by minimizing sensitivity to small errors. It makes algorithms more robust and it makes them more robust against changes in data. For instance, this is crucial in security systems or pattern recognition. So again, we're going back to the fact that it is only one bit is changing. So if you're trying to ensure that the security of the system is proper, or there's no anomaly or no errors, no breaking or something like that. Once you see that only one bit has not changed or something unusual has happened that you don't expect with gray code, then you know that there's a problem there. So it's also used in specialized imaging hardware. So it is invaluable in hyperspectral imaging and 3D scanning with structured light. So hyperspectral imaging is basically like an advanced imaging technique that captures a very wide spectrum of light for each pixel in an image. Normally, what we can see as humans is